Hey everybody, welcome back to our Materials Informatics series. Now, we just finished a video talking about ensemble techniques where we learned about random forest, AdaBoost, gradient boosted, all these types of decision trees that can help us learn properties using ensembling of techniques. Now, today we're going to introduce a new type of algorithm that can be used to help find patterns in our data and to make predictions, either classification or regression. And this is via what we call support vector machines, or SVMs. And these were all the rage in the 90s, right? Nowadays, everyone talks about deep learning and neural networks, but before those were around, these were the state of the art. They came after decision trees, and they were pretty powerful, and they remain really powerful tools. So they're a good thing to have in your tool belt of things that you can consider trying when you're building models to predict materials properties. So let's get started. How do these things work? To answer that question, let's begin by thinking of data that is one-dimensional, right, on a number line, basically. So for example, here I'm showing you density of some different materials, some insulators and some metals. Well, many insulators tend to be oxides. Oxygen's not all that heavy, whereas your metals tend to be metals, right, from, say, transition metal group. They tend to be heavier. So it stands to reason, plus these are more close packed, these tend to be more open structures, that the density is going to be different. Your metals do, in fact, tend to be heavier than your insulators. So you could then start to think to yourself, well, maybe I could actually classify whether something is an insulator or a metal based off of its density. And then if you did want to do that, then the next obvious question is like, okay, how should we go about making that decision? Clearly, all of our insulators are over here and our metals are over here. So maybe you could actually draw a line between those two sets of data and say, if you're below this point or above this point, we know that you're a metal or an insulator. So the trick is like drawing where this line is. Do you draw it right smack dab in the middle, or do you draw it somewhere else, right? If you draw it right in the middle, like this, then what you're doing is you're maximizing the distance between that threshold and these observations. So this is called a maximal margin classifier because you're trying to maximize this margin between your threshold and your observations. Okay, and this could be used, right? You could say from here on out, every time that you measure the density of something, if it's greater than about 6 or so, you're going to assume it's a metal. If it's less, then you're going to assume it's an insulator. So hopefully you see the problem coming because we have metals like lithium, which is quite light. Its density is really low, right? And you've got insulators, which are quite heavy, right? And so we're going to run up with problems, right? And that's exactly where the issue we get. Consider this scenario, right? Here you've got a metal which is really low, right? Maybe that's sodium or magnesium, whatever it is. One of these light metals. So now what do? Well, if you're still taking the maximal margin approach, then you would draw your threshold right between those two data points, right at, whatever that value is. But this isn't great because really that one metal is an outlier, right? It was an outlier. What are the odds, if you do this again and you get a measure a new data point, say where that green star is, do you really think that that green star is more likely to be a metal or an insulator? To me, looking at it, it looks like it's probably an insulator, and that one blue data point is an outlier, right? And that's the problem here, because if we drew it this way with a maximal margin classifier, this guy would be called a metal, but it might actually be an insulator, right? So this is a problem with maximal margin classifiers. By trying to maximize that margin and not have any errors, you end up misclassifying your future things. So they're just too sensitive to outliers. So this is kind of another over and over, whether it was linear models or whether it was decision trees, we've seen this trade-off that always exists between variance and bias, right? Here's yet another one. So the threshold made from outliers is just low bias, high variance. That's not good. So we need to do better. And doing better means that you're going to inherently allow it to misclassify some things. Instead, we can introduce a different threshold that allows some amount of misclassification. Like, what if you drew it here and you said, look, we know that we're going to misclassify that blue square right there. We get it. That one's going to be misclassified. But on average, we're going to do better overall by allowing some misclassifications. So instead of using a maximal margin, we're going to do what's called a soft margin, where we pick where that line, that red line, ought to be using cross-validation. When we divide our data up and we train on it, we try a bunch of different values and we pick the place for that red line, our threshold, such that we basically get the best overall performance, okay? So to do that, you're counting your misclassifications and your observations within the soft margin, and you just figure out the best performance overall. Okay, now this comes to the word support vector classifier, because the observations that are within this margin and the distance to the edges of your observations, that's called your support vector. So a support vector classifier is the name of this thing. So now you've got something that seems like it works pretty well. This was a sort of silly example because it's only one dimensional, and obviously we want to classify things or do regressions based off of higher dimensional data, not just one dimensional data. So how would this look in 2 dimensions? Well, if you've got 2 features now, feature 1 and feature 2, we do the exact same thing. Let's say you've again got 2 different classes of data, circles and triangles, and you want to figure out how to split those up. Well, since we're dealing with factors in 2 dimensions, our margin becomes something that is 1-dimensional as opposed to 0-dimensional. Before, it was a point on a line. So it was a single point that we make it, right? We basically said we're going to put the margin right here at a single point. So it was 0-dimensional. Here, the line of our classification is 1-dimensional. The margin is 1 dimension less than your data, essentially, right? Here we had 2-dimensional data and our margin is 1-dimensional. So we're going to draw a line. That's this dotted gray line here. That's what we're using to split our data. And then you have margins, right? You introduce margins on either side where you allow it to, you try and maximize those margins, but only within a certain point, right? If you tried to completely maximize them, we'd run up with the same problem we did before. So instead, we introduce soft margins and allow for some amount of misclassification, but better performance overall. So these points that are grayed in, filled in gray, these 3 points, those ones all got misclassified. But that was better than doing maximal margin, which would have done even worse, is kind of the idea if you did cross-validation on this. So that's pretty slick. It works in 2 dimensions. You could do it in 3 dimensions. This time, if you do it in 3 dimensions, your classifier becomes a plane instead of a line, right? Now you have a plane. And you can just keep on going up in dimensionality. You can have 100 dimensions and use it to split it. And our classifier would become whatever the features are total. Features minus 1 becomes the dimension of what we call our hyperplane, which is just a way of splitting it. And it's hard to visualize that because we're humans and we can't see that. But computers can do that, right? They can take all that data in and they can split it even in high dimensions. And that's pretty great, okay? All right, so this all seemed pretty hunky-dory and pretty rad, like a cool way to classify data, but it doesn't work very well with all data sets. Like take this one, for example. Maybe you have one data set where it's one type of class here, and then it turns into another class, and then it eventually turns back into that first class. From a material science perspective, this could be something like phase as a function of temperature. As you heat a material up, the phase diagram could indicate that it's going to turn into your phase of interest after a certain temperature, but if you go too hot, it's going to turn into another phase of maybe not of interest, or back to your original phase, right? That's possible. So how would you split this, right? Where do you draw it? Since this is 1-dimensional data, do you put the classifier right here? Well, then you misclassify all 3 of these. That doesn't seem great. Or do you put the classifier, over here? Then you misclassify all of those. So that's not very good either. So none of those are good options, right? Even if you aren't relying on a maximal margin classifier, even soft margins, you're going to have this fail. Your support vector classifier is not going to work. And this is where we now need a support vector machine, right? A support vector machine does something clever here, and it pseudo-transforms your data. What do I mean by that? Well, imagine that same data, right? These exact same data points. This time, I'm now going to increase the dimensionality. I'm going from 1D, I'm going to make it 2-dimensional by taking those exact same X points on this plot, right? These things used to be down here, right? That used to be where that triangle was. But we're now going to add a Y dimension. We're going to increase the dimensionality by saying that Y is equal to whatever X was squared. So this line here, the solid line, is Y equals X squared. By doing that, by changing its dimensionality through a transformation, we now see that it's possible to have a soft margin. We can have a soft margin classifier again, right? So this is really slick. Now if you draw that line, you can do pretty well to split your data up. So this type of transformation, this was a polynomial transformation, right? We went from X with just X data points, and we said now Y equals X squared. So it was a second order polynomial transformation of this data. It now allowed us to split the data. That was pretty clever, right? Well, then the next question is like, well, why did we do x squared? You could have done x cubed or whatever else, right? Here's that same data with x squared, x cubed. All of those were possible. So how do we know which one will be the best classifier overall? Which transformation will help us do the best job of splitting our data? That's where we have to introduce a systematic way of exploring different transformations. And that's where the machine comes in support vector machine. We're going to ask our algorithm to one by one go through all the different transformations which are convenient for us to try and calculate which one will produce a support vector classifier that performs the best for each one of these transformations. Now, these transformations have a special name. We call them a kernel. The kernel is what we're doing to our data. We're transforming it using some sort of kernel, okay? So you've already seen that there's a polynomial kernel, right? Where we basically do y equals x squared or cubed or whatever else. But there's other kernels. One of them, a popular one, is called the radial basis function. It's another popular kernel for SVMs. It's a little harder to explain. It's actually technically like it has infinite dimensions, which sounds gnarly. We'll show you briefly what that means in a moment. But in essence, it basically says when you get a new data point, let's say that your new data point is right there, that star, and you're asking yourself, well, should it be with the circles or the triangles when we classify it? The way that it does it is it takes into account its nearest neighbors with more weight than things that are further away. So since that thing is near to, you would calculate all of these interactions to every other point in this entire data set. You'd calculate all of those things, but you pay attention to ones that are closer to it more so than those ones that are further away, right? Hence why they call this the radial basis function. Maybe you've seen that in other parts of material science. It always has to do with, moving further and further outwards. Right, like a radius, right? So sometimes they call this a weighted nearest neighbor. It's similar to that, but that's another approach. It's another popular kernel that we can apply. So sometimes, often with support vector machines, you'll hear people talk about the kernel trick. The kernel trick. When I first learned about this, I thought the kernel trick was just this thing, like, oh, we can't split this data, but if we just add another dimension, all of a sudden we can. That seems pretty tricky to me, right? And it is tricky, it's great, but that's not the kernel trick. The kernel trick is the fact that you never actually have to do the math to transform your data, right? To do this transformation, if it's just y equals x squared, that's not too bad. But you could get to more complicated transformations. And if you're doing the math to actually transform every single data point with all those many different transformations that you're going to try, because you're going to try many of them and take the best, that gets problematic. That gets really hard. So the trick is that you never actually have to transform your data. But the calculations are done as if the transformation had taken place, and this greatly reduces your computational requirements. So you're saying, okay, but how? Well, you can show it pretty simply with the polynomial kernel example, right? So the general equation for our polynomial kernel is you've got your 2 points, A and B, but we're going to now transform them by adding some sort of offset plus r and then raising it to some polynomial value d. That's the general equation for the transformation. So if it's a second order transformation, then d becomes 2 and you could have some offset r. Well, you can point this out that, okay, let's say we do that. Let's pick 1/2 for r just because it's going to make it convenient here. And we pick 2 for our exponent. Well, then this thing, you can rewrite that simply as these two, right? We can deconstruct that multiplication into these two factors, right? We can factor it out. And then if you actually multiply those, you get a times b plus a squared b squared plus 1/4, which is the exact same as this dot product. Here's the trick, right? That dot product, if you dot product these two things with one another, you get that exact same outcome. So they're the same. Well, these two dot products, all of a sudden you have an x, a y, and a z, an x, a y, and a z for your 2 points. So you can measure distances between things. You can figure out all the math that you need to figure out for your classifier just by recognizing what your a, b, r, and d values will correspond to locations in terms of your x, y, z positions, right? So that's the kernel trick, is the fact that you don't actually have to do this math in the middle here. You don't have to. You just know that there's a formula that turns this general formula into spots, right? Positions. And that allows you to now calculate distances between points and all that jazz. So it's an easy transformation because there's no real transformation required. The same thing can be done with the radial kernel. It's just kind of gnarly. The general equation for the polynomial, that's supposed to say radial kernel, is exponential of negative gamma multiplied by the distance between a and b squared. Remember, they pay attention to distance. We pay attention to things more that are closer than further away. Hence, it has to take a distance here, and then it squares it. And then you multiply it by gamma, and that's basically something that is a learned parameter that says how much should we pay attention to how close something is. Should we really pay attention or give it some slack and look at things that are further away? That's what this gamma parameter allows us to adjust. Well, I'm not going to get into the math of it here. You can check out Josh Darmer's StatQuest video here, which is fantastic and goes through all the gory details. But essentially, this thing, you also can take a look at how this thing can be expanded. And then this can actually be represented as a infinite Taylor series. I mentioned once that this turns into a radial basis function, has infinite dimensions. That's because there's infinite terms in a Taylor series. And so that's essentially where that's coming from. In essence, what are your tunable parameters? Well, you have the Cparameter, which adds a penalty for each misclassified point. So this is how you're going to trade off between variance and bias. And this is typically values between 0.1 and 100. So you would search that space when you're tuning it. Then you've got this gamma value, and that dictates how much influence near neighbors should have. So a low gamma is going to put more data points together. A high gamma will put fewer points together because the radius becomes smaller. And this is typically, those between those values. So that is our support vector machine. Hope that was useful. They're pretty easy to implement. They are a little bit slower, just generally speaking, than decision trees because you can't parallelize aspects of these calculations, and some of these transformations, even the calculation distance with the kernel trick are still slow, so they don't scale well with data, but they're pretty good, and they're certainly something that you should have in your back pocket as you start thinking about which model to use to predict your data. Okay, with that said, in our next video, we're going to talk about extrapolation in materials informatics. Stay tuned.